right, let's talk about what this has to do with driving on the road. So this is a side view of a car that is rounding a curve. And think about what's happening here. The car is rounding the curve, so it has a tangential velocity, and it has a centripetal acceleration and a centripetal force acting on it towards the center. So let's talk about what's causing that. So think about, this is the road here. Okay, this is the road. And this is the center of the curve. So the car has weight acting on it, and it has a normal force acting on it. So what is providing the centripetal force? Well, the force that's actually pushing this into the road is the friction force. So in the y direction, all of the forces add up to 0, which means that the normal force has to be equal to the weight, which is mg. And in the x direction, there's only one force acting on it, and that is the frictional force. And that is providing, actually, let me restate that. All of the forces acting on it are providing a centripetal force. The net force is equal to the centripetal force. And the only actual force that's acting on it is the friction between the tires and the road, which is FF, which is FC. So FF is mu times Fn, and FC is mv squared all over r. And notice that mu mg is what Fn turns into, right? So Fn is mg, and that's equal to mv squared all over r. So notice that the mass factors out of this, and that means that, if I bring this down here, that mu g equals v squared all over r, that the speed that this car has to travel at under the specific conditions of whatever the coefficient of friction is and the radius of the curve, in order to stay in that curve, only depends on mu, g, and r, right? It's directly related to those, to the square root of those. So if I want to find the speed that this thing has to travel at in order to maintain and stay in the circle and not skid off in a line tangent, this is the formula. It has nothing to do with the mass, right? The mass is independent. So it could be a truck, it could be a car. It really only has to do with how rough the surface is and the radius. Well, the radius isn't going to change in bad weather, but mu will, right? So this is why flat roads are really dangerous when it rains, because all of a sudden mu goes down very, very low, and the speed that you can travel at safely on these roads will change drastically. Let's do an example. So one thing you'll need to be able to do is you'll need to be able to draw the vector diagram. So you've got a sports car. It's on an unbanked curve with radius of r 220 meters and a coefficient of 0.86. You want to know the maximum velocity that it can travel at. So you want to make sure that you would be able to draw FG, Fn, and FF. And you need to know that in the y direction, Fn equals Fg because it's in equilibrium. All the forces add up to 0. And in the x direction, it is not in equilibrium. All of the forces make it have centripetal force. So the biggest mistake people do is they call FF FC, which is true, but really the net force is the centripetal force. So of all the forces acting in the x direction, they add up to provide the centripetal force. And the only force acting in the x direction is FF, which is mu mg equals mv squared all over r. My m's cancel out. Notice it didn't give me this at all. Well, it didn't give me the mass at all, so I know it's going to cancel out. So V squared equals mu G times R, and V is going to be equal to the square root of 0.86 times 9.8 meters per second squared times 220 meters. So if we put this in our calculator, we have 0.86 times 9.8 times 220 equals, and then we need to take the square root of this. So to take the square root, we will do, let's see if we can find, nope. We want to do second, and we want to find the square root button, if we can find it on here. Well, another way to do square root is to take x to the 1/2. So if I press x and then I raise it up to the 1/2, that will give me the square root, which is 43.5, I think it said. I might be wrong about that, but it was 43 meters per second. So this is about as fast as you can take that curve. And if you go any faster, what happens is this friction is static friction. And we know that static friction is always higher than kinetic friction. So if you overcome static friction, if you go too fast around this curve, you'll overcome static friction, then all of a sudden you start to slide on the road, and now it's kinetic friction. So you have even less friction, and you can't gain control of the car, and it will skid in a line tangent to the curve at that point that you skidded at. All right. What if we wanted to know the coefficient of friction necessary to go a certain speed around a curve? So remember that V squared equals the square root of mu G R. Actually, it equals mu G R, sorry. Our diagram, once again, is going to have FG, FN, and FF. So we always want to draw a diagram of what's going on. And now we're going to just solve for the for mu. So mu is just going to be V squared all over GR. Well, we need to know V in meters per second. It's 30 miles per hour times 1 mile per hour on the bottom and 0.447 meters per second here, which is 30 times 0.447, 13.41. So this is going to be 13.41 meters per second squared divided by 9.8 meters per second squared times 200 meters. So if we put this in our calculator, it'll be 13.41 squared divided by 9. Actually, let me just clear that and move this over so I can see my formula. Yeah. Okay, so 13.41 squared divided by the quantity divided by the quantity 9.8 times 200 end quantity equals 0.0917. So mu is 0.0917. Notice there are no units to that. The meter squared and my second squared will cancel out because this is the coefficient of how rough it is. Oops. All right, so where were we? We are wow, I just did something weird to this. All right, there we go.